Okay, so in the last video, we calculated the pH of a buffer, which was made, quote unquote, the hard way, i.e. by partial neutralization. Partial neutralization being when we take acid, weak acid of course, and we partially neutralize it with hydroxide or a suitable alkali. But hydroxide is the normal one. Why? Well, if we think about a buffer, we're going to have HA, which is our weak acid, and we are going to have A minus, which is the salt. We have large concentrations of both and a very small concentration of H plus. By doing partial neutralization, that is what we get. And we calculated that the moles of the acid in the buffer was 0.012, the moles of the A minus, in this case ethanoate ions, was 0.013. The total volume of the buffer when we added the two bits together was going to be 38 cm cubed, and the pH of the buffer was 4.80 to be precise, in that with pHs we always give 2 decimal places. Now, what do we want to do in this video? What we want to do in this video is see what happens to that pH if we add a small amount of strong acid. We're only going to be adding strong acid or strong alkali, or indeed a little bit of water, i.e. dilution, to our buffers when we do calculations. And remember, the definition of a buffer is it is a solution that resists a change of pH upon addition of a small amount of acid, alkali, or water. Resists, it's not magic. It doesn't just keep its pH the whole time. So, in just a sec, we're going to see another question appear, like so. So what does the new question ask? What happens to the pH of the buffer when 1 cm cubed of 0.5 molar, 0.5 mole per cm cubed hydrochloric acid is added? Okay, so we're adding acid. First off, you can have yourself an idea of what's going to happen. We're adding acid. Therefore, the buffer is going to get more acidic. We would expect the pH of our answer to be slightly lower, i.e. more acidic than our original, and our original was 4.80. That's what we would expect, so we can check what's going on. Buffers are not magic. They will not maintain an exact pH, but they will resist a big change in pH. Okay, so what do we need to do for calculation? Well, as with most calculations, first things first, work out moles of something. So, moles of HCl added is going to be 1 over 1,000 times 0.5. That's 5 times 10 to the minus 4, which in this case I'm also going to write out as 0.0005. Now, I know we normally leave things in standard form, but it should become abundantly clear in a moment why I'm doing so. So let's have a quick think about what is going on. Well, we have CH3COOH in the buffer. This is reversibly dissociating to give H plus ions and A minus ions, but we've got an artificially large amount of A minus ions, so CH3COO minus, we have an artificially large number of those because we partially neutralized our acid to make the buffer. So what do we know? Moles in original, I'll just write orig buffer. Well, what have we got from the previous question? We've got 0.012 of that. We've got an amount of H plus, but it's very small, and that is what we're trying to calculate. So unlike a lot of equilibrium calculations where we have numbers for everything in the equilibrium, we don't actually have a number for H plus here, so we'll just leave that by the by. And the A minus, the CH3COO minus, the ethanoate 0.013. Okay, so what's happening? We are adding acid. What's going to happen to our position of equilibrium? Well, the Cheerios Principle says that if we add something to a system in equilibrium, the position of equilibrium will move so as to reduce the imposed change, i.e. use up what we've just added. So we are going to be using up H plus ions. Something I should have put up earlier, that this, actually both of these numbers, are also the moles of H plus, because we have a monoprotic acid. If we were using sulfuric acid, you would have to double those numbers. So be careful, because that's a really nice little exam question, a really nice trick for an examiner to do. Anyway, what's going to happen? Well, we are adding H pluses, so we are going to move to the left hand side. We can assume that all of the H pluses we add due to the acid being added are used up. We can assume that, okay? Which means that our moles of ethanoic acid is going to go up. You're saying, just a minute, we've added hydrochloric acid. Why is our moles of ethanoic acid going up? Because we have got ethanoate reacting or recombining with these H pluses to form ethanoic acid. So this is going to go up, and it is going to go up by 0.0005. And I took that's why I took it out of standard form. It's going to make this calculation easier on the eyes and easier to run through. What's going to happen to the ethanoate ions, the A minus? Well, we're moving away from them, so their concentration is going to go down. We are using those up to react up the new H pluses that have gone in. So this is going to go down by 0.0005. So where does that leave us? Well, that leaves us with moles in new buffer. This is why all of your labels are so important in new buffers. Don't know why I pluralize that. Let's just write buffer. That makes more sense. Okay, so what's that going to be? 0.0125, because it's gone up. This is going to be 0.01. It's also going to be 25. That's coincidental. That's just the way the numbers worked out. That wasn't actually intentional, but it will make life a little bit easier doing our calculations in a moment, only because we'll only have to do the calculations once. Now, let's have a think about what we're dealing with. We are now dealing with the solution. We want to work out concentrations. We have added more solution to our original solution. So we need a new volume. What is our new volume going to be? Well, our original volume was 38 cm cubed, to which we have added 1 cm cubed. So we're going to have a new volume of 39 cm cubed. Not a massive difference, but enough to make a difference in the numbers. Okay, we are going to be working out a Ka style calculation. Remember, Ka in this case is going to be H plus A minus, but we'll write it out in full because we don't have a great deal to write out, so we might as well, over CH3. This is the acid, COOH. Right, we can't make any assumptions about H plus concentration equaling A minus concentration, because we are not dealing with a weak acid, we're dealing with a buffer. H plus up here, way smaller than the HA or the A minus concentration. So what we do need is we need our concentrations. So let's get a different color pen so we can see what we're doing. So let's have new acid CH3COOH concentration. What's that going to equal? That's going to be, well, concentration is 1,000 moles over V, so that's going to be 1,000 times 0.0125 over V. What's our new V? Our new V is 39. Okay, and that's going to equal 0.32. Now, I told you we were going to have a little bit of free marks here because the moles of the A minus of the salt in there happens to be the same as the moles of the acid, so that is going to be saving me some calculator battery. Okay, now remember, that's not always the case, and even if it is the case, it is worth writing it out twice for the examiner. Now, we need to rearrange. Let's just change pen again so we can see what we're doing. We're going to rearrange, get H plus, always rearrange. Before you substitute. Should be pretty straightforward. We've done this a number of times. That's going to equal 1.7 times 10. Put my 1 in there. 10 to the minus 5 times 0.32 over 0.32. Again, write it in. It is part of the sum. We all know that's going to disappear. It's going to go to 1. It's going to disappear. But that's not the point. We need to write it in. Equals 1.7 times 10 to the minus 5. Again, write it in. It is a marking point. It is part of the answer. Therefore, if we do our pH is minus log to the base 10 of the H plus concentration. This is going to be come out as 4.772 decimal places over. Now, let's just double check that. It started out at 4.80. We added a small amount of acid. And guess what? It got slightly more acidic. So, as I said, you can tell if you are ballpark. If you are getting this roughly right, you can see that you are in the right ballpark. So, buffers, not magic. Their pH will change. It just won't change very much. So, run this through again for yourself. Have a look at it. And do some more questions like it. Get practicing. Get good at it.